So let's continue. So here you got the velocity error constant as limit s tends to 0 s into g of s into h of s, or your steady state error for a unit ramp signal. You got the steady state error as 1 by kV. Now let us see how much is the steady state error for a type 0 system. So for a type 0 system, your kV is equal to limit s tends to 0 s into g of s into h of s, right? So now you can calculate this error constant kV, that is equal to limit s tends to 0 s into k into the general form of your g of s. S in s plus z1, in the numerator you will be having the zeros, s plus z1, s plus z2 into etc. divided by s plus p1, because this is a type 0 system, so s plus p2, etc. So once you substitute s equal to 0 here, you will be getting the answer as 0, right? Therefore your steady state error ESS is equal to 1 by kV, that is equal to 1 by 0, that is equal to infinity. Understood? Therefore we can conclude that for a type 0 system, when the input is unit ramp signal, the steady state error is infinity. For a type 1 system, let us see for a type 1 system. So here your kV is equal to limit s tends to 0 s into g of s into h of s. Therefore we can write this as g is equal to limit s tends to 0 s into k into s plus z1 into s plus z2 into s plus z3, etc. divided by, here this is a type 1 system, therefore it is s into s plus p1 into s plus p2 into etc. Once you we can cancel out this s and s, and if you apply this s equal to 0 here, you will be getting the total value will be equal to, or we will be getting, it is nothing but k into z1 z2 z3 etc. divided by p1 p2 p3 etc. So this is nothing but a constant. Therefore we can calculate your ESS as ESS equal to 1 by kV. This is nothing but a constant. Therefore we can conclude that for a type 1 system, when the input signal is unit ramp signal, there will be a constant steady state error. Understood? So let us see what is the steady state error when for a type 2 system. See here, for a type 2 system, your kV is equal to, as usual you can calculate limit s tends to 0 s into g of s into h of s, right? It's a unity feedback system, therefore you can write this as, which is equal to limit s tends to 0 s into the numerator polynomial s plus z1 into s plus z2 etc. divided by s into s square into s plus p1 into s plus p2 etc. Why this is s square? Because it is a type 2 system. This is general form of a type 2 system. So we can cancel out this s and s. So and if you apply s equal to 0 here, the denominator will be equal to 0. Therefore your kV will be equal to infinity. Therefore your steady state error ESS is equal to 1 by kV, that is equal to 1 by infinity, which is equal to 0. And for the higher type of system, or if the type number of the system is 2 and above, it is 2 and above, then the steady state error will be equal to 0, because the value of your velocity error constant kV is equal to infinity, and therefore for the any type of system which is having type number 2 and above will be having a steady state error of 0 if because the kV or the velocity error constant is equal to infinity in this case. Understood? So now let us analyze the steady state error when the input is unit parabolic signal. So here steady state error when the input is unit parabolic signal. For a parabolic signal, so here we can calculate the steady state error as ESS equal to limit s tends to 0 s into R of s divided by 1 plus g of s into h of s. Now parabolic signal, therefore the value of R of s is equal to 1 by s cube. This is what the input, the Laplace transform of your input. Therefore we can calculate the steady state error as ESS is equal to limit s tends to 0 s into R of s is 1 by s cube whole divided by 1 plus g of s into h of s, right? Or we can write this as, which is equal to limit s tends to 0 1 divided by, right, s square plus s square into g of s into h of s. Or we can write this as, which is equal to 1 by limit s tends to 0, because once you substitute s equal to 0 here, this term will be equal to 0. Therefore the remaining things are limit s tends to 0 1 by g of s into s square into g of s into h of s. So what is this limit s tends to 0 s square into g of s into h of s? It is nothing but your acceleration error constant. Therefore we can write this as 1 by k suffix a. This is nothing but your acceleration error constant, right? So the quantity ka is nothing but limit s tends to 0 s square into g of s into h of s. Already we have seen about this, right? Now for a type 0 system, let us calculate the steady state error. The input here is parabolic input. If it is a type 0 system, then Ka, the acceleration error constant Ka is equal to limit s tends to 0 s square into g of s into h of s. So as usual, now you write the standard form of your g of s, so that you will get a limit s tends to 0 s square into s plus z1 numerator polynomial s plus z2 into s plus z3 divided by s type 0 system. Therefore s plus p1 into s plus p2 etc. Okay, now this is equal to, once you substitute s equal to 0, numerator will be equal to 0, therefore the entire quantity will be equal to 0, so that you will get Ka is equal to 0, and therefore your steady state error ESS is equal to 1 by Ka, which is nothing but 1 by 0, which is equal to infinity. Therefore for a type 0 system, for unit parabolic input, your steady state error is infinity, right? For a type 1 system, let us see the same steady state error for a type 1 system. So for a type 1 system, you just calculate the acceleration error constant Ka. Your Ka will be equal to limit s tends to 0 s square into g of s into h of s. Or we can calculate this as g is equal to limit s tends to 0 s square into k into, now this is a type 1 system, therefore s plus z1 into s plus z2 into s plus z3 etc. divided by s into s plus p1 into s plus p2 into s plus p3 etc. So now once you substitute s equal to 0 here, you will be getting, right? So here s square is there, you can cancel out this s square and this s. So if you substitute s equal to 0 here, right? So you will be getting k into so this value will be equal to 0. So numerator will be equal to 0, therefore this value will be equal to 0. Therefore your steady state error ESS equal to 1 by Ka, which is nothing but 1 by 0, which is equal to infinity. Therefore for a type 1 system also, you are getting the steady state error as infinity for a parabolic input. Now let us see for the type 2 system. So here the acceleration error constant Ka equal to limit s tends to 0, s square into g of s into h of s, right? Or we can write this as, which is equal to limit s tends to 0, it is a type 2 system, therefore s square into k into s plus p1 s plus z1 into s plus z2 divided by s square into s plus p1 into s plus p2, etc. Right? So this is nothing but we can cancel out this s square and s square, and therefore you will be getting which is equal to k into, once you substitute s equal to 0, you will be getting k into z1 into z2 into z3 divided by p1 into p2 into p3, etc. So which is nothing but a constant. Right? Therefore your steady state error ESS will be equal to 1 by Ka, which is equal to a constant. Right? Therefore for a type 2 system, the input, if the input is a unit parabolic signal, then you will be getting a constant steady state error. So for higher order system, for example, if the type number of the system is equal to 3, so let us analyze that also. So for a type 3 system, your Ka will be equal to limit s tends to 0, s square into g of s into h of s. So in this case you will be getting the value as infinity, and therefore your steady state error ESS will be equal to 1 by Ka, which is equal to 1 by infinity, which is equal to 0. So if the type number goes beyond 3 or beyond 3, then of course the steady state error will be equal to 0 for a unit parabolic signal, because the value of the acceleration error constant Ka will be equal to infinity in this case. So let us see some of the problems related to this type of error constant. So let us see first example. So you have given an unity feedback system with a open loop transfer function OLTFS. G of s is equal to 10 into s plus 2 divided by s square into s plus 1. Here in this case you need to find the position, velocity and acceleration error constants, the different error constants. So they have given the open loop transfer function of an unity feedback system, and also you need to calculate the steady state error when the input R of s equal to